So this is the Physics Dialogues, and today we're going to be talking about all things quantum. I know some of you may have joined last week for a quantum discussion as well. We have a large group, so we split it over 2 days. I'm going to do the same very brief introduction this week as last week, so bear with me if you've seen it before. But then we'll have a whole new set of speakers telling you about some of the quantum physics research that's going on at the University of Sydney. So thanks for coming. My name's Stephen Bartlett. I'm a professor in the School of Physics. I'm a quantum information theorist, and I work also as part of the Sydney Nano Institute and the AOC Center of Excellence for Engineered Quantum Systems. So first, let me just give you a very brief and quick overview of quantum information processing, and that includes quantum computing. Quantum computing is not everything in quantum information, but it's a good example of the type of things we're talking about. So I'll say quantum computing quite a bit here, but it applies to all types of new ways of processing information with quantum systems. And what's really exciting here is we have very good evidence to believe that if we could build information processing devices, computers, out of quantum systems and make them behave quantum mechanically, even on a very large scale with large numbers of qubits, that they will be able to do things that are out of reach with conventional computers. So that's very exciting, and it obviously has the potential for a huge impact on our world if we can build such a quantum computer. The challenge for the physicist is that quantum systems are very prone to errors and noise, and we have to find a way to correct for these errors if we want to make a quantum system behave on the macroscopic scale with, maybe millions of qubits that you might need for an interesting computation. We need to find ways to correct or eliminate those errors. And we need to do that both with theoretical ideas and in developing the actual hardware that will implement these devices. The hardware is absolutely in its very early days, but we're starting to see out of a whole range of groups, including here at the University of Sydney, some early devices that can really be called quantum computers. They involve really now a sophisticated interaction of very low noise quantum systems and several of them. It's still early days. You can't run huge, interesting algorithms on them yet. But there's a feeling at the moment that we're at an inflection point for the field, that things in the next few years are going to change very rapidly. Let me give you just in one slide a taste of maybe how to think about how or why a quantum computer might be able to do something that a classical computer cannot. So we've all heard of Heisenberg's uncertainty principle. This is one of the foundational ideas in quantum mechanics, that we must be uncertain about some aspects of a quantum system. That's just not that we haven't bothered to learn those things, but it's an inherent uncertainty that's a property of nature. That quantum uncertainty. And in a quantum computer, we force that uncertainty to be about what computational path the computer is following. We don't know exactly what it's computing. It's in fact computing many different computational paths at the same time, in some sense of the word. Many computations are occurring simultaneously. That's sort of a quantum-y type of concept now applied to computation. But that's not enough. What we need to do at the end of the computation is to use quantum interference to amplify some of those computational paths and suppress others in order to get an answer that we want, and an answer that we couldn't have got just by classically sampling one of those paths on its own. Now, if that sounds a bit vague, any explanation of quantum computing necessarily does so, because at its heart, we really don't understand how it's working. And that's much the same way as we don't understand Bell non-locality. So we can explain in quantum theory that quantum particles are non-local, that they can't be explained in a classical picture. You can prove that with mathematics, but to really explain what those quantum particles are doing is a challenge. And we feel that it's the same idea with quantum computation. The maths is clear. We should be able to get an advantage, but really what's going on is one of those quantum mysteries. If we could build a quantum computer at a large scale, we think we can do amazing things, but we're still quite unclear about what are the limits and the power of such a device. Here's a range of different ideas, areas where we have some good evidence that quantum computing can play a role. But we probably won't know the full answer to these questions about a quantum computer's power until we build bigger devices and we can play and hack with machines. And we're just starting to get to that point with the types of early stage devices that we have today. Okay, so that was a whirlwind introduction to the field. Let me give an equally brief introduction to quantum information science in the School of Physics at the University of Sydney. And I'll just tell you about some of the research groups, those who you're going to hear from today and some of the others that you maybe heard from last week. I'll mention first of all that we're all based in the Sydney Nanoscience Hub, which is an amazing state-of-the-art facility for doing quantum information science research. Amazing labs, amazing fabrication and characterization facilities there. We have a number of experimental groups. So you may have heard last week from John Bartholomew, who runs a quantum integration lab. Here he's looking at the interaction of quantum light and quantum matter that will be used in connecting together quantum devices over some sort of quantum internet. We have the quantum control lab where they are using ions trapped with electromagnetic fields and manipulated with lasers to build quantum computing devices. I'll just note that there's a fantastic success story of a spin-out company, Qcontrol, coming out of that group. You will hear today from Torsten about the Quantum Nanoscience Lab, which is in partnership with Microsoft. And I won't say anything more about that now because Torsten will give you some details. We also have a very vibrant theory group that works closely with the experimental team and also thinks quite abstractly about these challenges in understanding quantum computing. You'll hear from Arne Grimsmo and also Robin Harper today about some of the things that are going on in the theory group. So I won't mention any more about that now. And as a final slide, just to give you a sense of all the different things that we're involved in and working with at the University of Sydney, we're part of the Australian Research Council Centre of Excellence for Engineered Quantum Systems, which is a national collaboration to develop quantum technologies. We're part of the Sydney Quantum Academy, which, as you can tell, is based in Sydney to offer all sorts of excellent training opportunities and research opportunities for the next generation of quantum scientists and engineers. And we have these partnerships with companies like Qcontrol, with Microsoft, and some others to really see our ideas translated out of academia and into the real world. And that's the end of my part. I'm going to stop sharing and hand over to Arne for the next part.
Okay, thanks for that, Stephen. There are no questions in the chat yet, so just to remind everyone, you can unmute yourself and ask questions, or if you prefer, you can just ask them in the chat. And after each speaker, we'll try to answer whatever you ask. Let me just share my screen. Let's see, just remove this. Okay, so as Stephen said, I'm a member of the quantum theory group, and I'll be talking about this emerging field that we call quantum electronics, which is one of the things we focus on in the quantum theory group. So first of all, what is a quantum electronic circuit? Or maybe a better way to ask the question would be, when is an electronic circuit in any sense behaving quantum mechanically? So this story started in 1980, basically, when Anthony Leggett, who's a Nobel Prize winner in physics, asked this very interesting question. What experimental evidence do we have that quantum mechanics is valid at the macroscopic level? So if you think of the rules of quantum mechanics, you know, the postulates, there's nothing in there that says that quantum mechanics is somehow only valid at the microscopic level, you know, single atoms and single photons and so on. But in the first 6 decades of you know, after quantum mechanics was discovered, there was no actual experimental evidence that it holds across you know, larger scales. And this question was posed by Anthony Leggett, and that kind of spurred on a very active period of experimental work to try to find such evidence. And it turns out that one of the most best sort of platforms for observing quantum phenomena with microscopic degrees of freedom is in electronic circuits. So specifically in 1985, using a superconducting circuit, energy level quantization, which is a genuinely quantum phenomena, is observed. So I won't go through in too much detail what happened in that experiment, but I'll give you kind of a flavor of what they discovered. So let me consider one of the simplest circuits you can think of, namely an LC circuit. So it's pretty much the simplest circuit where you can store electromagnetic energy. And from classical physics, the prediction is that the energy of this circuit has 2 terms basically. The first one is the energy stored in the capacitor, where V here is the voltage across the capacitor. And the second term is the magnetic energy stored in this inductor, where I is the current. And classically, classical physics says that the charge on the capacitor oscillates, which means that also the direction of the current through that inductor oscillates. However, one of the basic predictions of quantum mechanics is that energy should be quantized. And specifically, in the case of electromagnetic energy, one quantum of energy is called a photon. So basically, according to quantum mechanics, the allowed states of this circuit should be states with discrete number of photons. So 0, 1, 2, and so on photons. And the energy should just be the number of photons times the Planck constants times the frequency of oscillations in this harmonic oscillator. When I say that that's the allowed states, I mean that's not exactly the correct statement. It's really these photon number states span the allowed states. So a general state, can be a superposition of 0, 1, and 2 photons and so on. That's allowed by quantum mechanics. Now, even though quantum mechanics, predicts this to be sort of valid, in a formal sense, it's not something you observe, in your sort of everyday electronics, like your phone or something. You don't observe it being in a superposition of 2 different states with 2 different values of energy or anything like that. So actually observing these quantum effects requires a fair bit of work. And there are generally two ingredients that you need. First is superconductivity. That basically means that currents can flow through your circuit without resistance. And the problem with resistance is that, when current goes through a resistor, it heats up and emits photons. That's how a light bulb works, basically. And this is bad. It's very hard, almost impossible to preserve like a superposition state when you're losing photons. And the second ingredient we need is extremely low temperatures. So typically we cool these circuits to something like 10 millikelvin, which is, to give you some comparison, it's much, much colder in outer space, for example. And the reason for that is that, any physical system will equilibrate with its surrounding. But the colder we make the temperature, the slower that equilibration happens. So it allows us to do something with that system before it just reaches, this boring equilibrium state. And even though this is, sounds quite challenging, the state of the art has sort of advanced to a stage where this is actually quite routine now in many laboratories around the world. And in the building where I'm sitting right now, in the Sydney Nanoscience Hub, you have several labs where these kinds of circuits are cooled down to 10 millikelvin on a almost everyday basis, and it's completely standard to observe and manipulate superpositions, other quantum phenomena like entanglement, wave function collapse, and so on. Okay, so I want to go on to kind of the next chapter. So in the early days of this quantum electronics field, it was all about, asking fundamental questions about quantum mechanics and microscopic degrees of freedom. But the real, one of the main reasons we're very excited about this field today is that it's one of the most promising platforms for building quantum computers. So how can you encode a qubit like Stephen was talking about in such a circuit? Well, once you have these quantized energy levels, it's pretty straightforward. You can, for example, define your logical zero, the zero state of the qubit, to be the state with 0 photons. And similarly, logical 1 can be the state with 1 photon. And then a general state of a qubit is a superposition of these two. Quantum logic gates can be performed by applying voltages to the circuit, so as a voltage across the capacitor, which, by the way, if you were here last week, this is actually exactly analogous to lasers in trapped ion qubits. And similarly, readout just amounts to measuring the number of quanta, or in other words, measuring the energy stored in the circuit. So I want to give you kind of a brief outline of the evolution of this field. So as I already said, it started in 1985 with this experimental evidence of quantized energy levels. Now, observing quantized energy levels is quite different from actually being able to control the states, the quantum state of the system. And it took more than another 10 years to actually be able to do that. So in 1999, we can say it was the first time that we actually had a qubit, in the sense that you have these two states, 0 and 1, which you can prepare in an arbitrary superposition. And then it took about another 10 years to go from 1 to 2 qubits, basically. So in 2009 was the first demonstration of a 2-qubit quantum algorithm. So I put that in quotes because it's a very small algorithm when you only have 2 qubits, but you can say it's the arguably the first sort of superconducting quantum computer. And then another 10 years later, the number of qubits have grown to about 50. And in 2009, there was this sort of breakthrough result of what's called quantum computational supremacy. So that just means that it's a quantum computer that performs some computational task that we believe is too hard for even the most powerful classical supercomputers today. A small caveat to that is that it's not, what was done in that experiment is not actually a useful computational task. It has no practical applications, but it's some computational task that you can do on a quantum computer, which you can't do classically. So it was a big milestone. Now I want to end with sort of one of the problems we're very interested in the quantum theory group. So since the beginning of the field of quantum computing, actually, one of the absolute sort of central challenges is that it's very hard to make quantum systems that are robust to noise. So for example, in the case of these circuits, one of the basic principles of any physical system is that it wants to reach its minimum energy state. And in the case of these circuits, that means that photons will basically be lost over time, so that you will decay from 1 photon to 0 photons stored in your circuit. This is actually analogous to spontaneous emission in atoms and what people call quantum jumps. Of course, this means that the information you store in your qubit is basically erased, and it basically prevents you from doing quantum computation of any substantial length. So in practice, this happens on a time scale of a fraction of a millisecond. And that's why quantum computers today are sort of very, very limited. So to make an analogy with classical computing, in a sense, we're still in the vacuum tube era, if you like, of quantum computing, where our basic components are very fragile and sort of constantly get corrupted. So one of the things we're really interested in the quantum theory group and that we're working on is trying to come up with something like a quantum analog of the transistor. So a quantum system that's has two states, 0 and 1, that are extremely stable and where you can do logical gates on very fast timescales. And I think it's a very interesting, exciting sort of time to enter the field, because we're in this period with very rapid development and we still have these very hard unsolved problems. So if you like theoretical physics and math, but you also like kind of creative problem solving, you should join our group and help us solve this problem. So that's basically my last slide. So I'll take questions if there are any. I'll just stop sharing. If there are no questions, I'll just hand over to Torsten. Thank you. Next one.
I'm start sharing my screen.
There's a question from Alex, actually.
Okay, then go ahead and answer the question first.
Yeah, go ahead and ask your question, Alex. Why were there 53 qubits in Google's system? That was basically, I think there are two answers to that question. There were sort of some theoretical arguments that you needed about 50 qubits to be able to do something that a classical computer can't compete with for this specific problem that they solved. So they needed to have at least 50, and 53 was basically as much as they could do. They just, that's the boundary of this, the state of the art right now. Actually, they made 54 qubits on the chip, and one of them was broken. so we're just at that boundary. Probably next year, the number will be larger, and it will continue to grow year by year.
Okay. I guess I'll take over. So I'm Torsten from the Quantum Nanoscience Lab, here as well in the Sydney Nanoscience Hub, as Stephen mentioned. And I will talk to you about nanodiamond as a theranostic agent for medical imaging, which probably sounds, first of all, not quantum, but you will see probably that it is. But first I will start to introduce the group on a bit broader range. So the head of the group is Professor David Riley. And you heard probably before, so he's on one side a full professor at University of Sydney, and on the other he's as well a full-time employee by Microsoft. So a lot of the research going on in our group is naturally based on quantum computing, and in detail on how to scale up the quantum computers. So if you think of, you have more and more qubits, so the whole infrastructure to address single qubits and to read them out and manipulate them is more and more challenging, because as you heard before, they have to be all in this dilution fridge, as you see here. So you need to bring in RF lines and all kind of things. And so a lot of the research is about where to interface the qubits at various
Did Torsten just fall out, or?
Yeah, I think
so.
I think we'll have technical problems.
Maybe we should move on to the next speaker.
There were a few people dropped out there, I think.
All right, maybe I'll pause the recording.
I was introducing the research which was done with Microsoft part, and I just started with the idea of what we do with the nanodiamonds. So we want them as a ferronostic nanoparticle. So the idea is you have a very small particle, you can have some imaging agent around, or you make it targeted with some certain enzymes to then you inject it in a body and you want to image it in some sense, or see where it's gone. And we want to do this with nanodiamonds and combine it with C13 MRI. And why do we want to use diamond? So first of all, diamond is non-toxic, so it's a really good biomolecule, if you want so. The other thing is diamond is used in a lot of various spin quantum sensor applications. So you can combine these and add now another level to it. And so, for example, you can use certain spins in diamond to detect electrical and magnetic fields. And here you see, for example, an idea that you put a nanodiamond on an AFM tip and then you scan it around, and so you will map the magnetic field, or you map single electron spins on the surface of other materials. It's as well used for quantum information processing and so on. So you have this whole variety of different things within the same system. So what is magnetic resonance quickly? So you in principle apply a magnetic field. So this will cause your nuclear spins to align. But as the energy gap for nuclear spins is very small, so at the fields at least what you can apply in an MRI machine, so you will get only a tiny spin excess, which is depicted by this one arrow more up than all the others down. So, and this little tiny thing is what you will use to make all these known MRI images everyone has seen before. So where you get contrast, where you have hydrogen, and depending on how much hydrogen is there, you have dark or bright regions. So now we want to do this with C13. So C13, the problem is you have only 1.1% abundance. So instead of like in the hydrogen, which is spinful to 100%, you have only 1%. And there is another problem, the so-called gyromagnetic ratio of carbon is much lower than that for hydrogen. So if you just take these numbers, you would think you see that your signal, what you would expect in an MRI, is a factor of 400 roughly smaller than the hydrogen signal. And that assumes you have the same amount of carbon. Now our idea is, of course, you want to inject a tiny, small amount of these nanoparticles, which you want to track and to image. So it's really unlikely that you will be able to see a signal at all. But the Boltzmann statistics tells us how this polarization is set up. And it depends on temperature and magnetic field. And it's plotted here for various things. So in red is for carbon-13, which we are interested, for comparison how the hydrogen is, and for electron spins. And you see it's plotted the polarization over temperature, and this is at a 3 Tesla magnetic field. So you see that when you go like below 1 Kelvin, you will see that the electrons are fully polarized. So that will give a huge signal. Nuclear spins, unfortunately, have much lower polarization, still at even 1 Kelvin. But in principle, you can see you can either decrease the temperature or you can increase the magnetic field to get more spin excess. So, or with other words, more polarization, and this will allow you to measure a bigger signal. So here are just some numbers again for various temperature. So a first approach to do a kind of hyperpolarization, which just means you want more polarization than you normally in a thermally in the thermal case what you would have. So what we thought is we have all these dilution fridges for the quantum measurements. So let's put a nanodiamond sample and just cool it down at a magnetic field. And this is what we did for 4 days at 4 Tesla. We had a diamond sample in this dilution fridge sitting at around 30 millikelvin. And so we think, okay, we got a really big signal, but now we need to measure it. So we have to get it out. And here you will see how that's done. A little fun experiment to pull a really cold sample out of the dilution fridge and then into an NMR machine to detect the nuclear magnetic resonance signal. And you see as well that there's quite a bit of teamwork involved. So you want to do this quick because you don't want to lose the polarization during the transfer. Yeah, and here it goes into the NMR magnet, and there it's where our signal is then detected. And here you see the comparison what we got. So you had 4 days at 4 Tesla, 35 millikelvin, and you got this purple line. And you see you have 6 times bigger signal than you would have after 12 hours in a 7 Tesla magnet at room temperature. So it's somehow working, but it's not ideal. And if you go back to the Boltzmann statistics, you would have expected a much bigger signal. So we lost a lot during the transfer. But can we do better? And yes, we can by using quantum again. So now we're doing a more quantum approach. So we're using electrons in the diamond, and they will be close enough to couple to our nuclei, to the carbon-13. So we're talking now about a coupled nuclear electron system. And this will give us these 4 energy levels. And by just using certain transitions, we will be able to create the spin excess I was talking about. So we have a magnetic field, and then we drive as well this transition, for example, and then we get relaxation into this state. So this will pump, in principle, our spin excess and will give us a positive signal and a negative signal on the other. And so this is our enhancement, what we would expect. To do so, we need, of course, to apply now microwaves. We need everything in a magnet. We want to do NMR. So there's a lot of extra components which we will need, and they're all drawn up here. And so here is then the result within this polarizer. And you see now we have really high signals. So the enhancement is now close to 500 times for a certain type of diamonds. You can see as well that it works for various diamonds. And the important thing, if you do a small calculation, you can see that your expected enhancement over room temperature is in the order of 30,000. So that's a big signal. So can we use this signal now to make something more useful in the medical sense? So we thought, okay, let's try to put it into a mouse and see if we can image it inside a mouse. So a real image instead of just doing these signals in the hyperpolarizer. So to transport this, and as you saw before, we lost quite a bit on the brute force approach. We needed a lot of extra magnets and other things to keep this polarization happening or staying alive. And we needed an MRI probe and shielded it with extra magnets. We had a magnet where we put the mouse, and then we needed a needle to inject, obviously, the diamond sample, and so on. And here's then finally the result. So we were able to do this and to see a diamond signal. So the diamond signal is the color-coded, the red and yellow one overlaid over a normal hydrogen MRI of the mouse. And that's in principle all I wanted to tell you about this bio approach of using quantum sensors, in this case nanodiamonds, or the spins within nanodiamond. And yep, happy to answer questions. And here you see the group. Thank you. And I hope I didn't drop out again.
Yeah, no, we heard you fine.
Sorry for that.
There's one question in the chat. I don't know if you can see that, Torsten.
No.
I can just read it out. So it's from Patrick, and it's, does the effect rely on the diamonds being anti-ferromagnetic?
No, it's not. So it's really these extra electron spins. They come from impurities in the diamond. Yeah. So usually the most common is that instead of a carbon atom, you have a nitrogen atom sitting at the diamond lattice, and this will provide you an extra electron. And the nuclear spins is just the natural abundance. So normal C12, what you have in diamond mostly, is spinless, so it has nuclear spin 0. And then you have C13, the isotope, with 1.1%, which is spin half. And so now you just couple these two and you create your polarization.
And then there's a question from what advantages would this imaging have over traditional MRIs?
It just gives you an extra channel. So usually you want to, for example, image a certain disease, like a cancer area or something. But very often you don't have extra contrast for this. So because you're just measuring hydrogen, doesn't allow you to distinguish these two areas. Now, if you modify your nanoparticle that it will bind more to a cancer cell. Very often cancer cells have higher metabolism, for example, so they will take more cells in, or they will have certain channels open which other cells don't have. So you can make that targeted, and so they will attach to more likely to cancer cells. And now if you're able to make them bright, to make them appear in the image, you can overlay them and you know, okay, this is where my cancer is. Or you give them a different function and you check for something else. All this is for the biology people, and we are more how to make them visible. But just to give you an idea.
Okay, and last question before we continue from Jake. That's, I think, more of a theoretical question about quantum computing. Are there any theoretical limitations to how many qubits we can contain within an arbitrary space? So he says he's aware of practical limitations with noise and other disturbance to the wave function, but the question is about, you know, if the experiment is perfect, is there sort of a mathematical, you know, more fundamental reason that we can't have, you know, there's a limit to the number of entangled bits in a given amount of space? Maybe I can try to answer. So one of the things we sort of say in like the same quantum information science is that information is physical, meaning that, you know, the limitations to computation and other information theoretic tasks are really, physical, because they have to follow the laws of physical laws of nature. And I guess in any qubit system that I can think of, every qubit has a certain size. So for example, an electronic circuit, like I talked about before, you can't make that too small. There's just a physical limit to that. Now then you can go to trapped ions, which are just atoms and much, much smaller than you can make such a circuit. But then you still have a physical limit to how densely you can pack the ions together, because you need to be able to have them interact when you want to, but you also need to decouple them. You need to put them further apart. Then you could say, okay, maybe something like photons. There's no limitations to how many photons you could put in, some amount of space. But to do quantum computation, again, you need to have sort of a controllable way of making them interact and not interact with each other. And the way that's typically done with photons is having them sort of sending them down waveguides and having them interfere on beam splitters and things like that, which means that the beam splitters put some limitation on the size. So I don't know if I have sort of like a truly fundamental answer to your question, but in any physical qubit platform that I can think of, there are physical limitations just set by the physical system that we're talking about. So that's the best answer I can give, I think. Move on to Robin.
Yeah. I think Robin can start now. Thanks.
That's good. You can see my screen, okay, can't you? The PowerPoint. Yeah, terrific. Okay, so my name's Robin Harper. I work in Stephen's theoretical department, again at Sydney University, and QCVV, the Quantum Characterization, Verification, and Validation. It's quite a mouthful. It is basically what I work on. So what is QCVV? Well, in the world of quantum computing, there are a lot of sort of theoretical practitioners who talk about magic states, and some of them even talk about muggle states. What I'd like to think of as QCVV is the dark arts of trying to actually work out whether the quantum device is doing what you think it is doing. And if we're very lucky, we can also use this to try and work out what's going wrong within a particular quantum device. So although it might sound trivial to see whether or not it's working as intended, inside a quantum device, of course, we're going to have this delicate superposition of entangled states, and they collapse whenever you take a measurement. And so what you have to do is you have to look at the collapsed values when you're measuring it and try and work out whether or not the device itself was working as intended. So just now, of course, this is very interesting times to be in this field, because we're starting to actually move away from just the, as Arne said, the single or the two qubit systems, and we're now getting some very large devices. We've got large devices from Google, from IBM, Honeywell have got some large ion traps. There are photon computers that do computing on photons. Innsbruck have got large ion arrays. So we're getting large devices, and we need to know the noise on those systems. So why do we actually care about the noise? Well, there are two types of things that can be done with these systems just now. People are talking about using what they call noisy intermediate scale quantum computers to do things like, we can't use them to factor because they're too noisy for that, but maybe we can use them for things like quantum chemistry, or there's, various other things that we can use them for. And if we know the noise, and in some way we can mitigate the errors, or at least interpret the results from the measurements with the noise to actually get more accurate results. Then, of course, there's the sort of holy grail of fault-tolerant quantum computers, where we hope to use these sort of topological style of quantum error correcting codes, a little bit like that lattice Stephen was holding at the beginning of his introductory thing. In fact, Sydney is probably sort of leading the pack and showing how, if we know the noise in quantum computers, we can write these decoders that will allow us to tolerate more noise and yet still be able to do fault-tolerant quantum computing. What I really want to basically do is go through some QCDB, and I want to talk about the past. And by the past, I mean theory that was proposed a few years ago and is now commonly being used. The present, which is the theory which we are using just now. And the future is maybe where we're going to be going literally in the future, things that we don't know how to do yet. And that if people wanted to work in the field, this might be the type of thing that they're looking for. So very early on, we had something like quantum process tomography. Now it's process tomography because we're not so much just interested in the state of the quantum computer, but we're interested in the processes that are going on in it, like the gates that are happening, or basically the noise that is corrupting the whole, if you want, quantum computing system. So quantum process tomography, I mean, it's well known, and it requires, you know, it requires to know lots of information about the quantum computer. With 1 qubit, of course, this is completely tractable. It's just 16 numbers. 2 qubits is becoming slightly more difficult. And very quickly on, especially once we go to the size of a quantum computer, there is no way we could know all the information we know to be able to do complete process tomography. I didn't even know there was a word for that number. The other thing that has been more widely adopted is things that where we just get single measures as to how good a quantum computer is. And there are various things that we can do with that. There's like the fidelity of the channel, which is how close is it to the perfect channel, which is no noise when we're talking about characterizing noise. Or we can look at the purity of the channel, which is looking, are we in some way losing information that we can never recover? Or is the noise in the system just causing a sort of rotation out effect that maybe we can later correct? And then people have been looking at things like, well, maybe we can decompose the channels. So we've got a little bit of what we call depolarizing noise and a little bit of rotational noise. And this is the type of thing that, you know, is actively being used by experimental groups all around the world just now. So let's go to the present. So what are we doing in the present? Well, none of those measures, the single fidelity is not going to help you decode your quantum computer, and the tomography is impractical. So we're going to have to start using, we are using lots of different ideas. So we start, you know, for the more mathematically inclined, we'll use group theory and representation theory to show how we can actually use some of those protocols to extract more relevant information from the computer. There are ideas that are called shadow tomography, which is like the reconstruction, not just of one, but of many quantities by using classical processing. So we have a whole lot of measurements we've taken on our quantum computer, and in analogy to, you know, like a 3D shape casting a 2D shadow, we use things like semi-definite programming to be able to reconstruct lots of figures of merit that might help us diagnose what's happening in the computer. And, you know, that's the type of people with computational complexity is very important in that. We can also use things like Bayesian learning and inference, and this is again something that we've been working on in our group, where we sort of use Bayes theory and priors to help us reconstruct, in this case, very large Hamiltonians that might have been affecting a system. And of course, that's in practice just now, where there's a collaboration we've done with UNSW, that's, you know, been helping them characterize what's actually going on inside their devices. Other work that we've done in the group is to use things like Walsh-Hadamard transforms, which are sort of an analog to Fourier transforms, to get an exponential amount of information out of the quantum computer. And we can use that to do things like work out when the whole device is being used, whether or not there are correlations across the device. But there's still very many open questions with that. For instance, when we're running it in the 2-qubit system, which you can see here, some of these dots should all be the same size, and they're not, which means that there's some very interesting noise processes going on in this actual device that was used to construct that data. And so that device was actually from the IBM quantum experience. And again, this is part of the reason why it's such an interesting time. Just now, people can get onto an IBM device, which is a noisy intermediate scale computer, and actually run programs on it. And of course, we use it to test a whole lot of our noise protocols. And the same thing with Google. Google are about to open up their large Sycamore chips and various other chips, and Honeywell are going to go on cloud, and I think Innsbruck, and a whole lot of people are going to be making their devices available for us to test our ideas on. It's the real time where theorists can start getting their hands a little bit dirty and actually test the ideas. And if that's the type of thing that interests you, then it is a very interesting time. But of course, having to deal with real devices brings its own complications. And so, for instance, in the current IBM devices, any protocols or ways of trying to characterize the noise requires that you take into account the fact that not all the qubits are equally connected. And so they have some weird qubit-to-qubit couplings in those devices, which are designed to counteract noise, but they do still need to know exactly what type of noise is going in the system. And that's kind of where we're working at just now, being able to efficiently characterize devices of this size. Now, of course, when we said there's a lot of noise, there is a lot of noise. So for instance, in a 14-qubit system, there are, even if you just assume that you've got the simplest type of noise channels, which are the type that we can enforce, there's still 2 to the 28, so roughly 28 million different things that you might want to measure to see whether they're going wrong. But of course, some of those are going to be very small. I mean, the 28 million numbers still have to add up to 1. So maybe the type of thing that we should be interested in are those that are above a certain amount. And this is an example of how we can use ideas from compressed sensing and sparse estimation to try and pull out the largest numbers, so that even when we've got a noise floor, which would be the fact that we can only take a certain number of measurements, we can still recover what the underlying error rates are to a high amount of fidelity. That's where we are. So these are the type of things that I'm hoping that we'll see all the experimental groups using in the next few years. But what about the future? Well, when we look at for instance, the Google machine, it's got over 50 qubits. So even though we can maybe extract an exponential amount of data, we can't actually even write it down. So with 2 to the 50, that's too large a number for us to hold in memory. So one of the things that we're thinking about in the future is how we can actually represent those machines using compact and accurate models. And sort of graphical models and graphs are maybe, so this is future speculative work, is maybe something that we can do. So up on the top is a model that actually represents the 14-qubit machine when it's run in single qubit mode very accurately. And it's something that only takes, say, as you can see, 96 parameters as opposed to the 16,000 we'd other use. But what graphical model to use? How can we use the data to drive the graphical model? And there are all sorts of ideas we can borrow from classical computer science, and there's all sorts of ideas that we can use machine learning to actually designate what type of model we want to use. And then there are other things that we don't really know how to deal with. Quantum devices are not stable, they drift. And so we need better ideas as to how we can measure drift in those intermediate and large devices. And so the field and how to do that is still not very well known. Also, we always assume Markovian noise, so that if I'm doing gate B, it doesn't matter what gate I did before I did gate B. But that's probably not realistic, and we need to have ways of characterizing, working out if there's Markovian noise in the system and how we can deal with it. So basically, there are a lot of challenges in QCD. It's a fascinating field. We need to be able to characterize the diagnostic information in current devices and, of course, larger devices. The type of information has to be useful to aid the creation of the devices and also to aid the making of fault-tolerant quantum computers. We still need to learn how to make realistic models of large devices from the data that we can get from them. We need to deal with time-varying and non-Markovian noise. And lastly, I think this is the biggest challenge of the field, we do need to find a better acronym. And that's it. Are there any questions? Sorry.
Okay, let's wait the questions for the students. I have a lot of questions, if I may.
Go ahead.
Well,
So I was just trying to keep us back on track, so I rushed through that a bit quickly.
thank you very much for sharing this fascinating research. And I think I have a, yeah, I said I have a, you know, a lot of questions, but I may put in one big question, and presumably there's to all of you, if you want to answer this. So, you know, my background is a particle physics, and also it's inherently quantum science and relativistic science and so on and so forth. All the experiments we are doing are based on the classical measurements, in essence. And, you know, it's essentially smashing the atoms, and that's a very, very expensive thing to do, as you know. But on the other hand, of course, we are talking, for example, in particle physics on a very, very weak signals hidden somewhere, and so on and so forth. So I was wondering whether all this development in quantum technologies, what is your take on, could be used for doing the measurements in particle physics, non-traditional measurements. I'll give you an example. It's on top of my head. For example, we know we are looking for this dark matter, and we are spending a lot of money for this. And the dark matter is all around us. We just need the sensors to sense them. You know, it's a big signal, and so on and so forth. The traditional, of course, measurements are very noisy, etc. But what is your take on general using these quantum technologies to look for, you know, the questions we are looking in particle physics?
I know that some people, for example, from the EQs, the engineered quantum systems, they have a project to look for axions with really precise quantum sensors. So they have these really precise resonator structures and can measure really precise frequencies. And if they would see any changes, I think they will be related then to certain interactions. I'm not an expert on this, but so they moved from to use their quantum sensor for particle physics to be able to at least exclude certain energy scales for certain mechanisms and things like this.
You're talking about the Mike Topos group.
Yes, yeah.
Well, that's another fascinating thing. We're discussing now that they can actually sense very high frequency gravitational waves, and they were asking us, you know, what is the origin of that? And there is a plethora of interesting physics in very high frequency gravitational waves. That's another example of it. Exactly. Yes.
Yes, and that's another. Yeah, the gravity sensor is, and
yeah. Well,
they have another stage where they just bring in quantum entanglement to make it even more precise.
Yes, so for example, the current LIGO detectors or plant detectors cannot reach those frequencies. For particle physics point of view, this could be, you know, indirectly reaching the scales, which is presumably some, you know, the 10 orders of magnitude smaller than what we are probing right now at LHC. So it's quite fascinating thing.
It is, yeah.
I'll add maybe one other perspective to that answer. So one of the big questions in the field is what are we actually going to use quantum computers for when we get them? And we don't really know, because it's not like every computational task can be done faster on a quantum computer. But actually one of the, I mean, all of these are sort of open questions and speculative, but one of the things people are quite optimistic about is actually simulating high energy physics. So, I mean, today, you know, you know better than me, but it's a big industry just simulating high energy physics on classical computers. But you can only get so far because it's basically, you know, computationally intractable once you get to certain, you know, strong interactions and so on. And people are quite optimistic that quantum computers can be able to go into a regime that's just completely impossible to simulate on classical computers. And then maybe you can, instead of doing the experiment, maybe you can just compute what is, or in addition to experiments, I guess you can compute what will happen.
All right, thanks. Okay, guys, are there any other questions or ideas?
Any suggestions for a better acronym for QCVV?
We need it.
All right. I don't see any further questions or topics for discussions from people here. Did I miss anything? Well, if not, then we presumably close today's session, and I would like to thank you, all of you, for sharing this fascinating research. And we'll have to continue talking about this stuff. All right, thanks everyone.
Thank you.
Oh, there is.